Hello everyone. In this video, we're going to talk about separable differential equations. So with a separable differential equation, what that means is we can separate the variables where we have all the x stuff on one side and all the y stuff on the other side. So let's look at a few examples. So let's say we want to find the solution to y prime equals x squared minus 4 times 3y plus 2. So we could rewrite the y prime as dy over dx. And that's going to be equal to x squared minus 4 over, times 3y plus 2. So let's separate. Let's multiply both sides by dx, and then let's divide by the 3y plus 2. So I'm going to have dy over 3y plus 2 equals x squared minus 4, and that's multiplied by dx. So now you see how I have all the y stuff on one side and the x stuff on the other side, which means I'm now in a place where I can integrate both sides. So for integrating the left side, we're thinking about a u substitution. We're going to let u be 3y plus 2. So du is 3, and we took that derivative with respect to y. So we would need a 3 here and compensate with a 1/3 out here. So now we're integrating du over u, which is our ln rule. So this is 1/3 ln, absolute value, 3y plus 2. Integrating the right-hand side, we're going to get x cubed over 3 minus 4x plus c. So I'm going to simplify this a little bit. Let's multiply everything by 3 to get rid of fractions. So we're going to have the ln of absolute value 3y plus 2 equals x cubed minus 12x plus 3 times c, which is a new constant. I'll call it c1. And then we could think about rewriting this as an exponential function. So we know ln is base e of the argument, and that's equal to the exponent. So my base is e, the exponent is x cubed minus 12x plus c1. That's going to be equal to 3y plus 2. And we could actually solve this for y. So let's rewrite this. We could rewrite this by undoing the addition that happened in the exponents. So we know when we multiply and we have the same base, we add the exponents together. So I'm going to undo that. If I multiply and I have the same base, my base is e here, I could rewrite this as e to the x cubed minus 12x times e to the c1. And that's going to be equal to 3y plus 2. Now, if I have e, which is just a number, raised to a number, that's a new constant. I'm going to call this guy c2. So I'm going to have c2 e to the x cubed minus 12x. And that's going to be equal to 3y plus 2. And so to solve this for y, I'm going to subtract 2 and then divide by 3. So c2e to the x cubed minus 12x minus 2 over 3 is equal to my y value. So there's my solution to the differential equation. Right now, it is okay to leave it this way. We don't have to solve for y. In some cases, you're not going to be able to solve for y, and that's fine as well. But this one, we could solve for y pretty easily. Let's look at the next one. We're going to use separation of variables again to solve. That should always be your first instinct if you want to solve a differential equation. You ask yourself, can I separate the variables? So let's look at this one. We have dy over dx is equal to 2x plus 3 times y squared minus 4. Now we have an initial condition, which means we will be able to find c. So I'm going to separate the variables. I'm going to divide both sides by y squared minus 4. I'm going to multiply both sides by dx. And now that I've separated, I can integrate. This left-hand side is going to require partial fractions. The right-hand side is going to be 2x squared over 2 plus 3x plus c. So I'm going to do partial fractions over here on the right-hand side. So that y squared minus 4 is the same thing as y plus 2 times y minus 2. So we're going to have a over y plus 2 plus b over y minus 2. So 1 equals a times y minus 2 plus b times y plus 2. So 0 equals a plus b, if I'm comparing coefficients of y. 1 equals negative 2a plus 2b, coming from comparing those numbers when I distribute. So my system of equations is going to look like this: 1, 1, 0, negative 2, 2, 1. And then when I do RREF, and I'm going to do that off on the side on my calculator, I'm going to end up with negative 1/4 and 1/4. So rewriting that left-hand side, we're going to have negative 1/4 over y plus 2 plus 1/4 over y minus 2, and we're going to have to integrate that with respect to y. Both of those are ln, so this is ln of negative 1/4 ln of absolute value y plus 2 plus 1/4 ln absolute value y minus 2, and that's equal to x squared plus 3x plus c. Now I'm going to clean this up. Let's multiply everything by 4. So we're going to have negative ln absolute value y plus 2 plus ln absolute value y minus 2 equals 4x squared plus 12x plus 4c, which is a new c. And then we're going to combine these. We have a rule that says the ln of a minus the ln of b is equal to the ln of a over b. So we have ln of y minus 2 minus ln of y plus 2. And that's going to be the ln of y minus 2 over y plus 2. And that's equal to 4x squared plus 12x plus c1. So I could rewrite this as an exponential function. So e to the 4x squared plus 12x plus c1 is equal to y minus 2 over y plus 2. Let me insert a new sheet of paper. So I have run out of room. Again, we can undo that exponent addition that's going on there by rewriting this as e to the 4x squared plus 12x times e to the c1. And e to the c1 is just another constant. I'll call it c2. So c2 e to the 4x squared plus 12x is equal to y minus 2 over y plus 2. And then let's multiply both sides by the y plus 2. So we have c2 e to the 4x squared plus 12x times y plus 2 is equal to y minus 2. So I'm going to distribute c2 e to the 4x squared plus 12x times y plus 2c2 e to the 4x squared plus 12x equals y minus 2. So now let's get all the y stuff on the same side. So I'm going to move this guy over here, and I'm going to move that 2 also. So I'm going to have 2 plus 2c2 e to the 4x squared plus 12x. That's equal to y minus c2 e to the 4x squared plus 12x times y. And I do that so I can factor a y out. The one thing I want you to notice on that left-hand side, I have a 2C2. I have not turned that into a new constant because I have C2s on both sides. I do not want to introduce a third variable with C3s and C2s because I only have one initial condition, and that would make things very complicated to solve. So to get y by itself, we're going to divide. So our final answer is going to be y equals 2 plus 2c2 e to the 4x squared plus 12x all over 1 minus c2 e to the 4x squared plus 12x. So now let's use that initial condition. Here's what we know. We know y of 0 is equal to negative 1, which means, oops, sorry about that. Which means x equals 0 when y is equal to negative 1. So we're going to have 2 plus 2c2. And I'm going to plug in 0. When I plug 0 in, that exponent is going to be 0. 1 minus c2. Again, I'm going to get 0 there on that exponent, and that's equal to negative 1. And the goal is to solve for c2. So I'm going to clean this up. We have 2 plus 2c2, e to the 0 is equal to 1, over 1 minus c2 is equal to negative 1. So we multiply both sides by 1 minus c2. So that's going to be negative 1 plus c2. If I were to subtract c2 by moving it to the left and then minus 2 to the right, I'm going to get c equals negative 3. So then our final solution, this is a particular solution because we found c, would be y equals 2 plus 2 times negative 3, which is a negative 6, e to the 4x squared plus 12x, all over 1 minus negative 3, which is a positive 3, e to the 4x squared plus 12x. Let's look at another one. Let's say we want to solve this one. So this one has t's and x's in it. It's going to work the same way. So we're going to have dx over the square root of 1 minus x squared, and that's going to be equal to the ln of t times dt. And then we are going to integrate. We have to think about how we're going to integrate each of these. So I am going to add a new sheet of paper because it looks like I'm going to probably need it. If I look at integrating the left-hand side, this is your arcsine formula. So this is going to be arcsine of u over a. So our u is x and our a is 1. So just arcsine of x. When I integrate ln of t, that is by parts. So I'm going to do that off to the side here. So we're going to let u be ln of t. So dv is dt. du is 1 over t dt. And if I integrate v, I'm going to get t. So integrating u dv is uv minus the integral of v du. So let's apply it. So uv, so t ln of t, minus the integral of v du. I'm going to have t ln of t minus the integral of 1 dt, which is t ln of t minus t. So t ln of t minus t, and then we're going to have a plus c there. Okay, notice I did not need absolute value around that ln. It was already in the original problem as just parentheses around that t with that ln. So let's plug in what we know. We know when t is equal to 0, x is equal to, when t is equal to 1, x is equal to 0. T is your independent variable here. So that's what I'm plugging in, and my x, what I'm getting out, is 0. So arcsine of 0 equals 1 ln of 1 minus 1 plus c. Arcsine of 0 is 0. Ln of 1 is 0. So 1 is equal to c. So then my particular solution would be arcsine of x equals t ln of t minus t plus 1. If we wanted to solve this for x, we could. We could take the sine of both sides. This is not going to be a pretty number here or equation, but it would look like this. X equals sine of t ln of t minus t plus 1. Let's look at one more equation. Suppose that population grows according to a limited growth model described by the differential equation dy over dt equals 0.1y, and it's subject to the initial condition y of 0 equals 350. We want to find the size of the population at time t equals 5, and we're going to round to the nearest whole number. So this is going to work the same way. We're going to separate the variables there. So dy over dt equals 0.1y. So dy over y equals 0.1t. 0.1 dt. And then we're going to integrate both sides. So we have ln absolute value of y equals 0.1t plus c. I'm going to rewrite that as an exponential e to the 0.1t plus c equal to y. Could use that trick again. E to the 0.1t times e to the c is equal to y. So C1 e to the 0.1t is equal to y. So you can see how this is an exponential model that's coming out of this. So now we've got to figure out what c is. We're going to use that initial condition. At time 0, the y value is 350. So e to the 0 is 1. So C1 equals 350. So we have the equation y equals 350 e to the 0.1t. They want to know what's happening at t equals 5. So 350 e to the 0.1 times 5. And when I plug that in, I got 577.05. And if we're rounding to the nearest whole number, that would be 577.